You're definitely familiar with water's freezing point, 32 degrees Fahrenheit, 0 degrees Celsius. But that's not the coldest water could be. Supercooled water is water that exists below that point. Scientists in a few labs have now made the coldest water yet. One team of researchers got the liquid water as cold as 230 Kelvin, and another down to 228 Kelvin, that's around -50 Fahrenheit, -45 Celsius. This is cool for science reasons alone, since this deeply supercooled region is difficult to probe with experiments. But there are other reasons. Water is weird and super important to understanding this planet we live on. And it doesn't always obey the rules you learned in high school. It can exist as a liquid at temperatures as low as -31 degrees Fahrenheit to 35 degrees Celsius in our own atmosphere, and it has strange properties that only get weirder at temperatures that cold. And right around these temperatures, it reaches a sort of weird mathematical kink, or singularity. Yet, what sort of singularity might water be approaching still represents an unresolved puzzle that has prompted the formulation of conflicting scenarios to interpret its origin, the authors write in one of the studies published last week in Physical Review Letters, lead by Ph.D. student Claudia Goy from the Institute for Nuclear Physics at Goethe University, Frankfurt. Another team from Sweden, Korea and Japan may have reached that singularity, and published their paper last month in Science. Here's a reminder, physicists use temperature as simply the average kinetic energy of a collection of molecules. Basically, the less the molecules move around, the lower their temperature. This isn't really temperature like stepping into the Arctic. It's describing the behavior of a tiny system of particles in a system built by physicists. Whether those molecules actually begin to freeze, or form the crystal depends on a host of other factors. It also requires an initial crystal, or nucleus, to form and begin attracting other molecules. Water prefers to be a crystal at temperatures below its freezing point, but scientists can build systems which prevent that crystallization. Some of water's physical properties are unlike those of other liquids, too. Think about how liquid water is densest at a seemingly random 39 degrees Fahrenheit, something that normally doesn't happen. Both teams created their own supercold water by shooting jets of tiny droplets into a vacuum. The smaller the droplet, the colder they'd be able to make it while still keeping it a liquid. Small droplets are also less likely to crystallize from foreign particles. Dividing into smaller pieces exposes more of them to the vacuum, leading to a strange kind of vacuum cooling. Essentially, lowering the pressure causes the particles on the surface to quickly evaporate off. This quickly removes the heat from the droplets and causes their temperature to drop precipitously. The droplets, when measured, record frigid temperatures. Measuring that temperature is difficult, too. Both experiments used laser pulses to measure the droplets as they traveled and evaporated in the vacuum. Measuring how the diameter of the water droplets change as they leave the nozzle gives the researchers a number they can turn into a temperature using a mathematical formula. This might seem like a roundabout way to measure temperature, but you cannot put a thermometer next to the droplets and say, okay, this is the temperature. Renato Torre from the European Laboratory for Nonlinear Spectroscopy, who was not involved in the research, told Gizmodo. Still, he felt that the methods used by the researchers support the claims in the paper. He also wondered if this would open a debate as to the most reliable temperature-taking methods in these experiments. As for the singularity, the group who got their water down to 228 Kelvin definitely noticed some weirdness. The water appeared to exist with two different density phases simultaneously, based on how clusters of a few connected water molecules stacked up in the droplets. Computer modeling demonstrated that this surprising result could explain water's weird density behaviors, explained Tim Wogan for Physics World. Paola Gallo from Roma Tre University in Italy called that experiment important in a commentary for Science. But another researcher, Alan Soper from the UK's Rutherford Appleton Laboratory, told Wogan that he didn't think one could draw detailed conclusions, and that perhaps the changes observed by that team were the beginning of the water crystallizing. They've clearly seen something and it's very interesting, he said, but what's actually causing it is probably something we don't have a straightforward answer to. Regardless, water is important. It's present in the clouds, in our tissues, and required to understand all sorts of phenomena present on our planet. And scientists are only beginning to understand its extremes. PRL, Science.